Thank you. Thank you, Sophia, for inviting me. And thank you, everyone, for joining us for this presentation. I'm Shashank. Today, I'll talk about training DBRX, which is Databricks' latest open source large language model. In particular, I'll talk about the key components, the key design components that went into the construction of DBRX, and what challenges we faced when we trained this model on large scale. So let's start off by comparing DBRX with other open source models. So comparing to Llama 270B, Mixtral, and Grok 1, we see that DBRX outperforms them on language understanding, programming, and math, and also having a good inference speed. So we see that as compared to Llama 270B dense models, DBRX is faster. Mixtural 8x7B is faster than it, but then you need to see the trade-off between like speed and the quality of the model. Now let's talk briefly about the training efficiency gains that we saw with DBRX. This slide has a lot of numbers, and I'll come back to talk about it in details later. But for time being, let's just compare these two models. So one is the MPT-7B that we trained last year. Has roughly 7B active parameters or total parameters. This is a dense model, and a much smaller version of the DBRX model. Let's call it DBRX MOEA. So this has the same architecture. It's just much smaller than DBRX, and it uses the same training data pipeline as DBRX. So we see that the combination of the mixture of experts model and our new data pipeline gives us almost a 4x win in terms of the number of training computation that we require. So you can train this model for 4 times cheaper or 4 times faster while having the same eval score. So Gauntlet is just an average of all the different eval benchmarks that we use. So this just means that they're roughly the same quality models. Let me explain the architecture a little bit. So the architecture of DBR it's a transformer model. It's a decoder only model, that is, it uses causal attention. And the key differentiating factor between this and normal transformers is that in the feed forward layers, we use a sparse mixture of experts architecture. Talking about the positional embeddings, we use rope, which are rotary embeddings. We compared so while deciding which positional embeddings to use, we compared it to the alibi, which is another popular embedding. But we ended up deciding choosing rope because even though rope and alibi showed very much similar performance and like on all the metrics and all the performance benchmarks, we ended up choosing rope because it has better hardware and library support, and also because rope is more widely adopted in the open source community, so we ended up using rope. In terms of the activation functions, we tried out a bunch of activation functions and ended up choosing Swiglu because it performed the best. Talking about the size of the model, this model has 132 billion total parameters and 36 billion active parameters. When you want to decide the size of the model, you need to think about two things: the model quality and the inference cost, because the larger your model, the better quality it will have, but also it will be that much more expensive for inference. So we ended up choosing this particular size because it strikes the right balance between model quality and inference cost. Um, and the model has a 32K context length, so it can process inputs of length 32,000 at once. And this was achieved by training it with sequence parallelism. Okay, so let me talk about the training overview quickly. So the first stage of training was called pre-training, where we train the model on tens of trillions of tokens. So these are just general data tokens, basically web data. The task here is just next word prediction. So you're training the model to predict the next word given all the words it has seen so far. The next phase, which is one of the key components of our data, like our training data pipeline, is the curriculum learning, which where we train it on hundreds of billions of high quality tokens, and we saw that this was one of the key factors that led to much better training efficiency. I'll talk about it in a bit in more detail.
What does it mean that 36 billion parameters were active?
I'll talk about this. This thing is something to do with the mixture of experts architecture. So what this means is that there are the total number of weights that are in the model are 132 billion. So you have that many weights that you can train. But given a particular input, we only activate 36 billion of those. So we decide which weights we will activate based on the input. So what this results is in that your model is actually quite large. It stores, you can think about it, stores a lot of knowledge in a sense. But when an input comes in, we only choose a very small subset of the model so that it's much faster and cheaper to actually run the model. So it gives you benefits of both the large and a small, like large model in terms of its um, eval metrics, knowledge, all that stuff, and small model in terms of its inference. So it gives you best of both worlds.
How do you determine the parameters to activate?
This is also something that we experimented with, and like there have been like other papers about it, like how what sparsity, because this is essentially the sparsity level, right? Like your sparsity is basically 36 divided by 128. So roughly speaking, only one-fourth of the model is active. Um, so yeah, this is something you experiment with and you see. You do empirical studies, you see what sparsity gives you a good balance of inference, efficiency, and quality. The next steps after curriculum learning are supervised fine tuning, which is where we train it to do instruction following and then reinforcement learning with human feedback. Basically, in summary, there are two key components of training efficiency that we had for DBRX. One is the architecture, which is the mixture of experts architecture that we used. And the second is high quality training data and curriculum learning. So now let's see the impact of each of these components. So first, let's see the value added by mixture of experts, right? So this is again the same table as before. So now let's compare these two models on the bottom. So the one at the very end is a dense model, which has 13 billion active parameters, and the one just above it is a DBRX, still a smaller version of DBRX, but an MOE model. And we see that they have roughly the same eval score. Like in eval, the higher the better. So they have roughly speaking the same like model quality. But we see that the MOE model got trained 1.7 times in like 1.7 times less compute. So that means almost you could train an MOE model with almost two times smaller computation or like two times faster and achieve the same model quality. And talking about the quality of your data, let's just consider two dense models. One is again the MPT-7B, which we trained last year, and again a new dense model, but we are using like high quality data for this one. In this case, we can see that you only need half the amount of data, like MPT-7B used 1 trillion tokens. This one used only 500 billion tokens, and we see that they achieve the similar eval scores, and yet the one which uses better data uses only half the amount of compute that MPT-7B used. So these two these two slides basically show the value, like the value of like the training efficiency that you get from mixture of experts and the training efficiency you get from just getting better data. Three components that decide your quality is the data, as we saw, the architecture, and obviously the amount of compute that you are able to throw in. So in summary, LLMs are reflections of your training data. So deciding your training data is crucial. So you need to answer questions like, what is the composition of your data on which you are training? How much code data is there versus how much text data is there? What are the sources of your data sets? And what curriculum are you using while training the model? And the second component is architecture. And we see that different model architectures have different efficiency. Mixture of experts are sparse models and they offer much better training and inference efficiency as compared to the classic dense models. And this is the reason why all the frontier labs, the latest models from frontier labs are using mixture of experts. For example, Google used mixture of experts model for Gemini 1.5 Pro. And once you have fixed your data and your architecture, then the quality of your model improves roughly as the log of the compute you spend. By compute, I just mean the amount of floating point operations that you performed for training the model. And this thing is called scaling loss, that your model improves roughly as the log of your the amount of training resources you spent on the model. Now let's talk in a bit more detail about mixture of experts. So this is how a mixture of expert model looks like. So each layer of a transformer um, has an attention layer, which is right here. And then in a normal model, you would just have one of these feed-forward networks. But in a mixture of experts model, what you have is like multiple of these. And then there's a router right in front of these, which chooses which of these experts to activate. So in a dense model, you would just have one of these blue boxes and no router. But in a mixture of experts, you have this router which chooses which one of these experts to activate depending on the input. This way, it actually adds structured sparsity because let's say you decide that 90% of your experts would be turned off for any input, then that means you have 90% sparsity in your model. Um, Hence, this way, MOE mixture of experts model have a large number of trainable parameters because all of these experts are actually trainable. You train all of them. But for any particular input, you only select a few of these experts. So that means the number of active parameters are much smaller. And the benefits that you get from this is faster training, faster inference, but the catch is that to achieve these two benefits, as we'll see shortly, you actually need to implement them carefully because if you implement them naively, you will probably not see these benefits that much.
How does Databricks model perform when comparing it to Llama 3 model?
Right. So when compared to the Llama 3 8B, I think DBRX is better. But when compared to Llama 3 7TB or 80B, yeah, I think it's 7TB, we are slightly behind it. Um, Yeah, so that's the comparison. So, like the comparisons that I showed, these slides are kind of old. So these slides were created when Llama 3 ATV wasn't out. But yeah, now I think Llama 3, I forget if it's ATV or 7TB. I think it's ATV or 7TB, whatever. 7TB. I think that's the best open source model, right?
But how does the router decide to which expert to route any given pass through?
Yeah, so that's a whole another actually a very interesting research area as well. So routers in general are just small neural networks. You can just think of them as a linear layer with a sigmoid at the end. Um, and it basically the output of that router is a probability distribution over each of these experts. So you take the input, you pass it to the router, which is like a small linear network, like a linear layer with a sigmoid. And the output is you treat them as the probabilities over these experts. And you just select the experts which have the top four or top five probabilities, and you send the input to those.
Thanks.
Yeah. And like, how do you train that router? How do you ensure that all the experts, like you don't ignore experts overall? All these things are important, like, and still active areas of research. And there are like many ways to train routers, many different even kinds of routers. So yeah, that's an active area of research.
What determines if tokens are high quality or not?
Like in the end, you can only decide if data is high quality if after you trained it with that data, you got a good model, like which performs good on evals. So that's like I would say the most difficult way of evaluating your data because you actually need to train the data on that. Like you actually need to train a model on that data to see if that's good quality. But you can do a bunch of other stuff. Unfortunately, I'm not in the data team. But I do know some things that you can do is one thing is you can just manually inspect data. And I've heard that um, that's the first thing you should do and you could do about it. Like just go through, randomly sample your data, see if the data makes sense, if it has noise or if it has content that you would not want your model to be trained on. And then you could think about pre-processing. Um, You could see if the output of if you're doing if you're messing something up in pre-processing. For example, let's say you're training on a lot of web data, and web has a lot of HTML tags, or let's say tables and stuff. So are you processing them correctly? Do you want uh, a lot of text data, oh sorry, tabular data in your training set? If you want, how do you want it to be structured? So yeah, that's a whole like in fact, that's a whole organization within Databricks that we have a data team that does all that stuff. So it requires multi-person effort to do all of that. Yeah. So in short, I don't think there's like one way to inspect and improve the quality of your data. You need to go through a lot of things.
Expert converts to a sparse tensor, and the router is choosing the sparse representation. Is this how it works?
So no, the expert themselves are not sparse. It's just the very fact that you, out of these n experts, you are choosing a few of them. That is what essentially is what we are calling sparsity, in that sense. The experts themselves are not sparse tensors. The experts themselves are fully dense. So each of these experts is a fully dense two-layer neural network.
Gitika, is there a qualitative recommendation to help determine the number of experts?
Yes, there have been papers that suggest what number of experts you want to use, and in general, we see that the more the number of experts you have, which let's say you call the granularity, so the more the number of experts you have, the better quality of model you get. But the problem is that the more experts you get, you start seeing more problems with respect to implementation and like just inference and training efficiency. Because in general, as I'll come in short in some time, you want for training and inference efficiency, what you want is well, not for inference, but for training efficiency, what you want is large input batches per expert so that you can use your GPUs fully. So like the key to GPU efficiency is having large matrix multiplications. So if you're training this model on a batch, and then each expert sees a large input batch, then you'll get good GPU efficiency. But if you have, let's say, a million experts, right, then each expert will only see on average a very small batch size. So you'll start seeing way low GPU efficiency than you would if you had a few number of experts. So you need to kind of trade off between two things, that more experts apparently, like in recent papers, people have shown that more experts lead to better quality models, but also with more experts, you'll get less training efficiency. So you need to kind of balance between those two.
When you're talking about training these, right, you're talking right now about training the whole network with all of the experts and the router, the entire thing in one go. Is there work going on or any guidance on, is it possible to train it kind of in a piecemeal fashion? That is to determine, maybe you train train the whole network a little bit and then use your router to pass over your training data to split it up into categories and then only train like one expert at a time on the data that it's most likely to be recommended from the router or schemes like that. Is that something that like is being done for training efficiency or being investigated, or it doesn't work? Or
I don't think there's a lot of work, or like I'm not familiar with a lot of work on that. But one thing I would say is routers do, so these routers operate on per token basis. So because like each expert, yeah, these routers operate on per token basis. So it's not usually the case that, let's say if you're training on like two different domains, let's say legal and medical, then all the legal things would go to expert one and all the medical things would go to expert two. It's much more on a per token basis how these experts are
I
chosen.
see. And so token to
Yeah.
token might have them go to different experts anyways in the middle of this
Yeah,
context.
right.
Okay.
Yeah, I mean, it could happen that if you have, let's say, code and English, then most of like the code word, like let's say Python keywords, they might go to a particular expert. That could happen, although I'm not sure if that actually happens. But also the other thing is there is something called upcycling, which people have started doing, where what they do is you first train a small dense model, and then you use that model to initialize a larger MOE model. So what you do is Imagine this, but let's say you have only, so if this was a dense model, you would only have one of these experts, right? Not all. So that is your dense model that you have trained. Now, what you do is to create an MOE model from it, you copy the attention head because that will remain the same. You copy all of these things, which will remain the same. And then you replicate the feed forward layer n times to create n experts. So initially, they'll be initialized to be identical. You can add a little noise to them while initializing. And that way you first trained a small dense model and used that to initialize a larger MOE models. This is something called upcycling. And there have been some papers which, like, there have been some recent works which do that. And in fact, some even like large language models which are upcycled from smaller dense models. So that could be something like you said, like a piecewise training where you first train like a dense model and then train an MOE model. But it's not exactly what you asked, right?
No, thank you for the elaboration. You clarified a few other things for me as well. Really appreciate it.
To go back
Thank
to
you.
something you said just a minute or two ago. So, I mean, is it a fair characterization to say that each of these experts is kind of an expert in a particular token?
Yeah, but like also you have to understand that as the layers go on, a particular token might lose its semantic meaning because, for example, this our model I think has 48 layers, um, or maybe whatever. Like let's say a model has 20 layers, right? So a token that starts off as like say the word car, right? That as the layers go on, it might be like the whole point of transformer is that like the words that come before it would also contribute to its semantics. So maybe in the first layer, it's always the case that the word car gets routed to the same expert, but as the layers go on, maybe that will change depending on its context. Like what are the other words in the same sentence?
What kind of curriculum learning are you referring to in the training data?
The simplest thing you could do in curriculum learning is you first pre-train on a large number of just moderate, let's say moderate quality tokens, and then you have uh, a smaller set of high quality data that you have curated a lot more. So that could be your curriculum learning. So the reason why you can't just train your entire like for the entire duration on high quality tokens is because you just don't have enough of them. So, for example, in this case, we had hundreds of billions of high quality data, whereas for pre-training, you need tens of trillions of tokens. So you just don't have enough um, high quality tokens to do curriculum learning. So the simplest thing you could do is you could get a smaller or like whatever the biggest size of high quality tokens you can. But there's a chance that even that would not be sufficient. So the simplest thing you could do is just get a high quality curriculum, like high quality data set, and that could be your curriculum learning data set. But also then you need to think about what the composition of that data set would be. Because like some recent papers, what they've done is they initially train with, let's say, a high percentage of text as compared to code. But as gradually the training goes on, the fraction of code increases and the text goes down. So that could be treated as a curriculum. Curriculum basically means you're changing the data set as you go on training. So a lot of it depends on what qualities do you desire from the model. Let's say if you want the model to be very good at coding, then you would want to increase the fraction of coding towards the end or like something like that.
When you say high quality, how do you judge something to be high quality or not?
The gold standard to know that this is high quality data is actually train a model on it. And if the model performs well, then you know that that's high quality. So that's like the gold standard, but that's also difficult to do because that requires you to actually train a model on that data. So then there are things like manually inspecting it or trying to train a smaller model on it. Just yeah, stuff like that. Also, sometimes if you can get like if you know the source of the data is good, for example, you would probably guess that data script from Wikipedia would be better than just from some normal, like some other website, because Wikipedia data would be more knowledge rich. It would not have grammatical errors, just stuff like that. So the source of your data is also a good indication of of your data quality.
Forward, and then the rest of questions we can address later.
Okay. Um, so yeah, so let's talk about the how MOE models how they speed up training. So in this blog by DeepSpeed, which is a really good blog, I would recommend, they show that with MOE models, if you train an MOE model to the same quality as a dense model, you could actually do that 5 times faster and with 5 times less compute. And on the other hand, if you so let's see what this plot says, right? So let's compare these two things. So you have a 350M dense model. So this is a normal transformer model with 350 million parameters. And then you have an MOE model with 350M active parameters. So the total number of parameters in this MOE model would be a lot more. But it's just that the number of active parameters are 350M. So we see that the loss that you get with the MOE model is much lower than the dense model. And if you implement it correctly, if your system is set up properly, then the training and the inference cost mostly depends on your active parameters rather than your dense parameters. I mean, not exactly, but you could get it to behave during training and inference as a 350M dense model in terms of um, inference costs, or sorry, training costs and training speed. So that's what we say here. So you can train a much better model with essentially the same training speed as a 350M dense model. And similarly for 1.3B dense and 1.3B MOE, you see that like there's a gap there as well. Also, inference for MOE models is faster. So comparing a dense and an MOE model of the so in this image is from the DeepSpeed blog. Comparing a dense and an MOE model, we see that MOE models are 9 times cheaper and 4 times faster, 4.5 times faster at inference as compared to dense models. And one key reason, so when I said that you can get these efficiencies if you implement it correctly, one key aspect of getting like actually realizing these improvements and these efficiencies is by implementing it in a way called expert parallelism. So why do we really need expert parallelism? So I think, as I said earlier, if you want to extract the most out of your GPU, if you want to get the highest efficiency from your GPU, you require large matrix multiplication. So the input to the GPU should be large matrices, ideally. This is a problem for mixture of experts because let's say you have k experts, right? And you're training on a batch of size n tokens. Then each expert, roughly speaking, receives n over k tokens. So that means the input matrix to each expert is much smaller. It's like k times smaller. And as we know, small matrix multiplications lead to hardware inefficiency. So one solution to this is expert parallelism. So let's say you also have exactly k GPUs. So you have k experts and you have k GPUs. What you do is you put one expert on each GPU. And then you route the tokens for that expert to that corresponding GPU. This is how it would look like, right? Like if you have two experts and two GPUs, you put expert number one on first GPU and expert two on the second GPU. And then after the attention layer, when you need to route the tokens to experts, all the experts that need to go to all the tokens that need to go to expert two, all of them are routed to GPU two, and all the tokens that need to go to expert one are routed to GPU one. So this way, what happens is each expert is still receiving n tokens rather than n over k tokens, and hence you get a large matrix multiplication. Hence you get like large input batches per expert, and you get like large matrix multiplications, and hence you are actually able to realize the theoretical speed up that you would have expected from MOE models. Does this make sense? This is like a subtle thing, but like also very interesting, I think. And another benefit of expert parallelism is that it also results in faster inference. As opposed to training, during inference, transformer models are actually memory bottlenecked. And this is because if you think about it, at inference time, you are only generating one token per step, right? So if you go to if you have ever interacted with like large language models, you type something, you send a query, and then it generates one token per step while outputting, right? And that means per step, the amount of computation is done is very small because it's only generating one token per step. So most of the time actually goes in moving the layer weights from memory into the GPU, and like stuff like moving the KV cache from the memory into the GPU. And so this is a problem for MOEs because um, if you have 8 tokens in a batch and each token goes to different experts, then you need to load all the 8 experts into memory. Whereas in a dense model, you would have to only load one of these like feed forward layers. For MOEs, you need to load all of these into memory. And that makes inference worse for MOE models because, as we have seen, it's exactly this movement which was already the bottleneck. So now you are even further slowing down the bottleneck. And the solution to this is again expert parallelism. So here what you do is you again put one expert on each GPU, let's say. So you have 2 GPUs. Put expert one on first GPU and expert two on second GPU. So now when you're loading the model weights into the GPU, first GPU only needs to load expert one and the second only needs to load expert two. So you're not like loading all the experts on all the GPUs. So this is what helps you realize inference efficiency gains in it. So like in short, expert parallelism is one of the keys to actually realize the efficiency gains that you would want from mixture of experts. So what are the challenges of training with expert parallelism? So as we've seen, now let's say in the simplest case you have one expert per GPU, right? But in reality, what happens is you do not route the same number of tokens to each expert. In fact, there's an imbalance almost always. So some of the expert would be more popular; they would be receiving more tokens than the others. So in that case, what happens is you don't know ahead of time how big of an input in terms of batch size you would see per expert. So what you need to do is you need to account for this dynamic memory usage because at each step, an expert could see different number of tokens. And what this means is different GPUs have different amount of computation that they need to do. So if one GPU is very popular and that received most of the tokens, that means other GPUs received much less tokens and they're performing much less work. And what that means is they're just sitting there idly. So, and this is not good. You don't want your GPUs to sit idle. So this white space is when the GPU is doing nothing. And in this case, this is probably because maybe it didn't receive enough number of tokens because most of the tokens went to some other GPU. And also, you need to allocate memory for worst case because if one expert becomes very popular and it receives most of the tokens, then it receives a huge input size. That means it needs to allocate a lot of memory. And in the worst case, that GPU might just run out of memory, and in which case your training would just crash and your training run would stop. And then you'll need to figure out how to fix that because even if you restart, again, that expert will receive a lot of tokens and it will again run out of memory. So now you need to figure out how to do that. And so the solution to this is usually you take this into consideration and you allocate memory in such a way. So you always keep some reserve memory so that you don't see these running out of memory issues.
So I have a question for the inference efficiency part. So you mentioned that if we have 8 tokens in a batch, then we need to load all the experts into the memory, and your solution is expert parallelism. It does solve some of the problems, but if you compare with the dense models, when you have 8 tokens in a batch, your MOE models still will have all the 132 billion parameters all in the activated status. And then compared to a dense model, for example, the Llama 3 70B, the total activated parameters are much larger, but the overall performance might not be as good as a smaller dense model.
Essentially, you are right that you are activating for this batch, you will be essentially activating all the parameters, but all the parameters do not live on the same GPU. So let's say those 130 billion parameters, let's say DBRX only had 2 experts. Let's say expert one was 70 billion and expert two was also 70 billion. So we are not loading both the experts on both the GPUs. So GPU one is only loading expert one and GPU2 is only loading expert 2. So essentially, each of them is only loading 70 billion worth of parameters rather than the full 130 B. In a dense model, you don't have experts. So like a dense model, you can't do this, but like in Llama 70B case, right? In Llama 70B, you would be loading the 70B parameters, which is the same as in this case if you apply expert parallelism.
But you can also use tensor parallelism for dense large models. In that way, for each GPU, the total number of parameters will be smaller.
Yeah, you're right. So you can also apply tensor parallelism on top of expert parallelism, if I'm not mistaken. And I think yeah, I'm not sure if I think we do that. Yeah, I think we do that. I'm not on the inference team, but like I think you can apply tensor parallelism on top of expert parallelism as well. So whatever you were doing with Llama, you could do the tensor parallelism on top of this thing as well.
I guess my core question is for the efficiency side, the bottleneck will be moving the memory, all the parameters from memory to the actual GPU computation part. And in this case, all the MOE models still have a much larger number of parameters, then this will become a bottleneck. Even if you do all kinds of expert parallelism or tensor parallelism, but if you consider the total number of parameters, then it doesn't change.
In this case, what
Right.
you also do is if you do something like imagine something like FSGP, right? So this GPU never had the whole 130B parameters. It only had 70B. Like this GPU never had the expert 2 on it. It only had 70B. I think like that's your question, right? Like
Yes.
GPU 1 would, yeah. So we never load the entire model on GPU 1 at all.
Compare with the dense model, if the dense model can also shard it for whatever method that only also load part of the memory on GPU. I mean, in this case, what's the advantage of MOE model versus the dense model, or how to?
Okay, so this is by faster inference, I mean faster as compared to a naive implementation where you would have had expert one and expert two on both the on like where you would have both the experts on both the GPUs.
Yes.
So yeah, I'm not saying this will be faster than a dense model. I'm just saying this is so when you theoretically think of how fast you could get, if you had done both experts on both GPUs, you would have gotten much slower inference. And like one way to actually achieve good inference speed is this. I'm not saying this is faster than.
Because in reality, that all the applications they care the practical inference speed a lot, then does the MOE model actually play a better role compared to dense model in the?
If you compare, let's say, an MOE model with 50 billion active parameters and a dense model with 50 billion active parameters, indeed, the MOE model will be slightly slower and for inference and training, but it won't be if you do all these like this expert parallelism and um, all the other optimizations, then it would not be much slower than the dense. But the benefit would be that that would be much better quality model. Like an MOE model with 50 billion active parameters will certainly be better quality than a dense model with 50 billion parameters. Whereas you are only like slightly slower than the dense model.
Oh, I see. I see. Okay.
Yeah.
Yeah, thanks for your opinion.
The challenges of large scale training. So when you scale up your training system, right, like the training complexity, roughly speaking, doubles or triples every time you scale up by a level. So the smallest scale on which you could train is like a single GPU. So the next scale would be training on multiple GPUs, but within the single node. Um, and then you could do multiple node training, and let's say the total number of GPUs is still not that large. Let's say less than 500 GPUs. And the next level of training is multi-node training with more than 1,000 GPUs. And DBRX was trained with 3,000 GPUs. And what I mean by doubles is like at every like going from single GPU to multi-GPU to multi-node to more than 1,000 GPUs. At each of these steps, um, roughly speaking, that the complexity doubles. You start seeing more failures. Um, the communication overhead becomes a problem. All these things which I will talk about in a bit. So yeah, what are the causes of these complexity that I was talking about? So firstly, about talking about runtime. When you scale up, you need to combine the parallelism strategies. So you need to have expert parallelism, as I said. You need to have a data parallelism, which is FLTP, which is like more than which is a special case of data parallelism. And then you need to have sequence. We also trained with sequence parallelism. So as you keep incorporating more of these parallelism strategies, each of these have their subtle things, subtle nuances that you need to worry about, and combining that with scaling up causes like problems. Also, you want to have efficient distributed training performance at scale. So the whole point of scaling up would be like to add more GPUs, and you would want your GPU to still perform at the same efficiency as a smaller scale training, right? Because if you double the number of GPUs, but let's say due to communication overhead, your GPUs are only performing at half the speed, then you didn't gain anything from from increasing the scale. Uh, so while increasing the number of GPUs, you need to ensure that per GPU efficiency is also maintained. So stuff like minimizing the communication overhead becomes very important there. As I mentioned before, for mixture of experts, you also need to worry about memory and compute imbalance between the GPUs. So these are just few of the things on runtime side that increase as that whose complexities increase as scale increases. Then there's the systems level. So the more GPUs you have, the more points of failure. That's just, that's a common sense. Like if you have more GPUs and each GPU has let's say, some rate of failure, then more GPUs means more rates of failures. Another problem that you start seeing is object store failures. So while training a model, you do regularly checkpoint it, and if the training run fails, then you need to download that checkpoint. Now, when you're training a huge model, it has like a huge checkpoint size. And if you're training it on 3000 GPUs, and each of those GPUs is sending download or upload requests to your object store, you can risk DDoSing your own object store. Your own object store can become overwhelmed by it. And then you also need to have good systems in place to monitor your run all the time and ensure fast auto restart. This is because if, let's say, your run fails every n hours and it takes m minutes to restart, then you need to figure out about how much time do you lose while restarting. And depending on these factors, you also compute what should be your checkpointing frequency. I mean, because in an ideal case, if your run never fails, right? If you're sure that it will not fail when you train it for like 2 or 3 months or whatever, like 1 month. And if it never fails, you don't even need to checkpoint if you're fully sure. You just need to checkpoint at the very end to get the final model. But that's not the real case. So you need to worry about these things, how frequently you want to checkpoint it. You can't checkpoint it too often because then you'll DDoS your own object store. So stuff like this. And so, in talking about hardware failures, the points of failures are the
Sorry, can I throw a really
GPUs.
quick question when you're talking about the software failures and all these methods?
Yeah.
Like I'm very familiar with PyTorch, or at least from like a user point of view, but it doesn't really have a lot of tools, it doesn't seem like, for managing um, big training runs and these kind of software failure issues. Like what libraries, what tools, what modules, like what do you actually use for handling this level systems? Or is it just like giant C++ databases from hell?
A lot of these tools that we use for scaling up and stuff like monitoring the run, checkpointing, all these things were developed by by Databricks. So yeah, unfortunately, you don't have a lot of uh, like unfortunately, we did not have a lot of support before. Um, Training DBRX, so we had to like implement a lot of these stuff ourselves, and a lot of these things are open source by us now. So you can find, for example, I don't think I have the slide about it, but we have a few frameworks that are in place that we developed and which are open source now. Stuff like Composer, streaming, Foundry, all these things are what we. So some of them are already. Well, they were already good enough that they could handle the scale, but still, when you go up to 3000 GPUs, you never know what component of your stack would break. So we kept improving all of those. And yeah, now those are open source. You could use them. It would have been ideal if all of this would be already handled by PyTorch or some other, let's say NVIDIA or some other library. But unfortunately, that was not the case. We had to develop a lot of these things ourselves. In the next slide, we'll see about that as well. So yeah, so when we talk about hardware failures, the point of failures are usually the GPUs, the switches, and the NCCL library. Um, so roughly speaking, a rough estimate would be that you see a failure every 1,000 H100 days. So since DBRX was trained on 3,000 GPUs, on average we saw roughly 3 failures per day. So the GPU failures scale linearly. If you have n GPUs, then the chances of failing scales linearly because you have n GPUs. But that's not the case with interconnects, right? Like with the communication between GPUs, because in the worst case, let's say, like let's imagine that you have n GPUs and each of them wants to communicate with each other. Then you have n squared connections between them, order of n squared. So now this scales much faster than n. So like you start seeing a lot of these NCCL, which are these communication libraries that GPU uses. So you start seeing a lot of failures in the actual communication as you scale up. So yeah, this is a meme that summarizes it quite well. So like, why is it that when a model dies, it's always one of these three? So it's either the bad cables, the NCCL timeouts, or dead GPUs. Um, and given this, like you can imagine if you're having 3 hardware failures a day, then a lot of time actually goes into debugging, resuming, and triaging, monitoring, all these kind of things. So in that case, you need to have an automated monitoring system. So like, for example, initially, when the run died, we had like a lot of people, a lot of effort, a lot of like, yeah, just also apparently this guy was vacationing when this run died and we had to involve them. Um, but then by the end of the run, it was so smooth that whoever was on point was actually sleeping when the node failed, and the system was automatically able to resume and restart the run. So all this happened during the training of DBRX. So um, yeah, so we learned a lot. Our systems improved a lot. We added a lot of features to our libraries while training this model. Yeah, so in summary, your model's performance is dependent on your architecture, data, and your compute. Um, Mixture of Experts is this new architecture that offers faster training and inference. However, it comes with its own implementation problems. And this, like everything I talked about, is still a very active area of research, and there are many exciting problems to work on this. Yeah, that's it. Thank you.
What are the canonical papers on mixture of experts LLM training?
There is not, there are like, yeah, there are a couple of like 4 or 5 papers that I consider are quite good. I could share them with Sophia after the talk. I have referred to a few of them here. Like, I think a very good place to start would be actually this blog by DeepSpeed. Um, this would be a great place to start with. DeepSpeed, yeah, by Microsoft.
I see a question from Bojana. Is there like a notebook or GitHub repo with open source code to do the mixture of training, mixture of experts training?
So just the Mixture of Experts part is implemented in this very nice GitHub repository called Megablocks, which used to be which we are like which Mosaic is now maintaining, but it's open source. So you can just go use it. It's called Megablocks.
Does curriculum learning continue pre-trained in terms of optimizer, or curriculum learning starts from scratch?
Yeah, that's a good question. For us, we use the same. It was essentially a second part of pre-training, so we didn't initialize it like we didn't reinitialize the scheduler from scratch, but rather just continued the same scheduler. Yeah, the same learning rate scheduler for it.
Also, question from Karina: did you try sliding window attention?
That's a good question. We didn't try it, but you could just do it for inference if you want to. But yeah, we didn't train it with sliding window attention.